Hello, my name is Antonio Laverghetta, and today I'll be presenting our group's paper on using transformer language models to predict psychometric properties. So psychometrics is a field of psychology concerned with psychological measurement, namely measuring latent properties like attitudes and personality traits. Now, models from psychometrics have become important in designing standardized tests of cognitive abilities. However, using these models often requires conducting extensive empirical trials, potentially involving thousands of human participants. So the goal of this work is to study whether we can instead use transformers as essentially standard replacements to human participants in order to assess a diagnostic psychometric properties were humans to actually take that diagnostic. So in order to study this, we use the GLUE benchmarks broad coverage diagnostic. This is a small manually created test set by NLP and psycholinguistics experts, which is meant to assess fundamental reasoning capabilities. So here are some examples of questions from the GLUE diagnostic. They are all formatted as NLI, or natural language inference. So essentially the model is given two sentences, a premise and a hypothesis, and it must reason about the relationship between those two sentences in order to classify them correctly. Now this NLI format is quite general, and the GLUE diagnostic uses it to assess for a variety of fundamental common sense reasoning capabilities. Questions are grouped into four broad categories: lexical semantics, predicate argument structure, logic, and knowledge and common sense. Given that the GLUE diagnostic aims to be comprehensive and the reasoning skills that it covers, we concluded that it was suitable for this set of experiments. So we gathered results on the diagnostic from a wide variety of transformer language models, all of which were implemented in the Hugging Face library. We used the SNLI, MNLI, and ANLI datasets to fine-tune these models, and we used their publicly available pre-trained weights, also available on Hugging Face. And using these models, we also experimented with various training regimes where we essentially varied whether the model had been pre-trained or fine-tuned before giving it the diagnostic questions. All of which was meant to essentially simulate the same diversity and proficiency we would expect to see in an actual population of human test takers. Some doing well on some categories, but poorly on others, for example. In addition, we gathered results from two baseline model types. The first was a set of BiLSTM language models, which use glove word embeddings. And the second was just a true random baseline. Now, of course, since our goal is to compare these models against human responses, we additionally needed to run a human study and have our participants take diagnostic questions. In order to do this, we first gathered a so-called attention check questions from the KSNLI dataset. Attention checks being one popular tool for assessing whether a participant is actually paying attention during a human study. Since the KSNLI questions had already been annotated by a large number of human workers, we concluded that if agreement on a given label in the data set was high, then that question was likely very easy to solve. We split our human study into multiple phases, each phase consisting of attention checks as well as actual diagnostic questions. We administered each phase as a Qualtrics survey, and we recruited our workers on Amazon Mechanical Turk. Now, in order to run quality control on our human participants' results, we developed a three-stage authentication protocol. In the first phase, we just looked for and removed multiple submissions, essentially. In the second phase, we looked at the workers' raw accuracy scores, and if the overall accuracy or the accuracy on just the attention checks was too low, we removed the workers' responses. And then at the last phase, we looked at the workers' justifications to each of their answers. As you can see in this example, for every survey question, workers had to briefly explain their rationale behind their answer choice. And we only accepted a worker's responses if their justification was deemed to be of sufficiently high quality. For further details on this process can be found in our paper. So in summary, after we performed these steps, we had gathered diagnostic responses from 27 human participants and about 240 language models, that being the total number from both transformers and the bi-LSTMs. So we began our experiments by looking at a psychometric measure called simple problem difficulty. This measure comes from an approach known as classical test theory. And it simply refers to how many members of a population get a diagnostic question or item correct. So we calculated this for every question in the diagnostic for each of our populations separately. And then we computed the Spearman correlation between the results obtained using the human participants and each of the artificial populations. And results are in this table. For the correlation between humans and transformers, humans and LSTMs, and then finally humans in the random baseline. And you can see that in the majority of cases, the transformers are achieving the strongest correlation of all of the artificial populations. And in many cases, the values are also statistically significant. Now, one important idea in psychometrics is that questions that rely on the same skills should also have similar chances of being answered correctly. And this is captured using a measure called inter-item correlation. Essentially, if the IIC is high, then it's likely that if the IIC between two questions is high, it's likely that those questions rely on similar underlying skills. So given this property, we reasoned that we could instead use IIC as a distance metric, and problems which relied on similar skills should cluster together based on this metric, where we represent questions as using the responses from each member of each population, humans, transformers, LSTMs, and the random baseline. So to study this, we turned IIC into a distance metric by simply taking 1 minus the reported correlation for a given pair of questions. And we used that to perform K-Mietowicz clustering on the resulting data points. Responses from each population was clustered separately. And then finally, after doing this, we computed the Pearson correlation between the results obtained using the humans and each of the artificial populations. And results are shown in this table. Similar to before, we see that in most cases, the transformers are achieving the strongest correlation of all models examined. Now, both of those previous studies relied on techniques from classical test theory. A more recent psychometric approach known as item response theory, however, is actually what is typically used when designing evaluation scales, because IRT is thought to be more informative than methods from CTT, because it allows us to model the properties of the diagnostic separately from the properties of an individual taking the diagnostic, essentially. So we wanted to see if our results that we previously obtained would also hold true using methods from item response theory instead. And we use we study the well-known RASH model, one of the most popular IRT models currently used by psychometricians. The RASH model, similar to classical test theory, allows us to gain estimates of each question's difficulty based on the responses from a given population. So we fit RASH models to each of our populations separately, similar to before, and we computed the Pearson correlation between the per question difficulty parameters obtained from the human population and again, each of the artificial populations. And results are shown in this table. And similar to the trend we've observed so far, in many cases, the transformers are again achieving the strongest correlation of all models studied. So in conclusion, based on these experiments, we believe that transformers have promising psychometric applications. It seems that they could greatly ease the difficulties on the part of psychometricians for assessing a diagnostic psychometric properties. But these results have also given us interesting insights into which underlying cognitive skills transformers appear to be deficient in. For instance, as you may have noticed, transformers consistently fail to achieve strong correlation on the morphological negation category, which we believe suggests an avenue with which they can be improved. Future studies are planned to scale up the size of these experiments by including more models and a much larger human population size, controlled for important variables like income and education level. So this concludes the presentation. Thank you for your time, and I'm happy to answer any questions you may have.